Okay, thank you. So let's see. So we'll talk a little bit about the wave activity in and below the Venusian clouds that we can see in the Venus PCM. So it's the same model that Thomas and Anton discussed, except that we recently changed the name. So now you have to get used to the Venus PCM planetary climate model. Okay, so let's go. The version I'm using here is the one that has been used for the latest tuning, done in the context of the Venus Climate Database, which is an ESA project, ESA-funded project that we've been developing recently to give you access to the GCM results in a useful way. So here on these plots, you can see on the left the temperature structure from the GCM compared to on the right the Viera Venus Express distribution. You can see that we can have the cold color quite nicely, except that it's closer to the pole. And for the zonal wind structure, I would insist on the fact that you can see on the middle panel that the GCM is still and always having the jets closer to the pole than in the observations. But otherwise, the vertical profiles of the wind field is quite nicely reproduced. All right, on the left, just you can see also the mean meridional circulation in the white contours. Okay. Now, what I do with the GCM is I take time series of different positions, and I will do first Fourier transform analysis to highlight the dominant wave patterns that we have in the GCM. So you can see on the, I will focus here on the cloud levels. So you can see that the dominant frequency is something about 4.3 Venus days. Oops. Ça marche maintenant. 4.3 Venus days, which is visible both in the vertical cut that you see on the left and on the horizontal cuts that you can see on the right, at cloud top level or in the middle cloud. On the left, you've got two different latitudes, 24 and roughly 62 latitudes. Okay, so I will just discuss this this wave pattern. On these plots, I want to show some filtered composite analysis. So what we do is do an average of this wave in a reference in a referential associated with the wave, and so you can see how this wave organized as a function of altitude. On the left, you've got the cloud top region, then on the right, the middle cloud, and on the bottom left, the cloud base region. So you can see how this wave pattern is mostly a wave number 1, and it's shifting its structure from something that looks like a Kelvin wave in the middle cloud and looks like a Rossby wave in the upper cloud. This can be also discussed compared with the Venus AFES analysis that was done by Takagi et al. In 2022. And this kind of wave in their paper is associated with Kelvin-Rossby instability. So I have a little bit of work to do yet to compare our results with their model, but I think there is a lot of similarities in these wave patterns between the two GCMs. This wave is a very important player in terms of angular momentum transport. You can see on the left the horizontal or angular momentum transport in the mostly in the middle cloud layer, between 10 to the 5 and 10 to the 4 Pascal here. So it transports angular momentum towards the equator. And in the vertical, you can see on the right, for the same middle cloud region, that this kind of wave transports a lot of angular momentum vertically, but mostly in the polar region. So these are different latitudinal parts of this wave activity that will transport horizontally or vertically the angular momentum. This is just the component for this wave. Now I want to go deeper in the atmosphere and investigate these are the waves that are visible at a deeper pressure. On the left, you've got 5.5 bar. So you can see, and on the right, you've got the latitudinal, the vertical profile as a function of frequency for 62 latitude. And in the orange circle, you can see the dominant part of this wave activity that is located mostly at high latitude. And but you have a component here on these simulations that we didn't see, in fact, in the 2016 paper, which is at the same frequencies, but so that are quite low and at the low latitudes. So the frequency, the dominant frequency here is around 20 days, Earth days. And in our work in 2016, and we discussed these waves as large-scale inertial gravity waves. Their structure is less clear here in these simulations than it was in the simulations back in 2016. And this is because these waves are really very sensitive to the profile of the solar heating rates in the deep atmosphere. And I will mention that again. Okay, so this is again the filtered composite analysis for these waves at 20-day period. And you can see their structure as a function of latitude and longitude, with mostly an activity in the upper atmosphere, in the higher latitudes, you can see these at two different pressures, 5.5 bars and 10 bars, so it will be deeper. And you've got also here, you see these structures that are mostly also wave number 1 or 2. For example, here it's mostly number 2 for the southern part of the wave, high latitude in the south. And so we need to do additional work to investigate these structures, which are again less clearly less easily analyzed than in the previous version of the GCM, where we had very clear signals of these inertial gravity waves. I will mention here the angular momentum transport. Again, these waves are the dominant player in terms of angular momentum in the deep atmosphere, and this reflects a lot on the vertical profile of the zonal wind. Depending on the activity of these waves, we will have a vertical profile of the zonal wind that is more or less enhanced in the deep atmosphere, and especially in the equatorial region. You can see that these waves transport angular momentum horizontally and in the equatorial region. So that would be the equatorial component of this kind of wave activity that mostly transport momentum towards the equator, around 10 to the 6 Pascal here. And on the right, you can see the vertical transport, which is done mostly at high latitude by the high latitude component of this wave activity. And in this case, you can see that it's located mostly above 10 to the 6 Pascal and not much below. And this ends up with a vertical profile of the moment of the zonal wind that is not strong enough in the deep atmosphere, I mean, the lowest 20 kilometers compared to the observations. And in previous version of the GCM, well, this wave activity could go much deeper into the atmosphere. In 2016, we had the same panel, and in fact, the activity is going very deep. And this is, again, I want to insist on this point because I think this is most important. It's very, very strongly sensitive to the solar heating ray profile and the way the sun can really heat the different levels of the atmosphere. And since we have a lot of uncertainty on these parameters, we can play a little bit about this. But this is really, well, I will finish on this, just insisting on this wave activity in the deep atmosphere really plays a significant role in the angular momentum transport and zonal wind profile in the deep atmosphere. And they are very sensitive to how the atmosphere absorbs the solar heating as we go down into the surface. Thank you very much.